So today we're going to talk about measures of dispersion. And when you think of dispersion, like if I were to look at this class and tell you all to disperse, you would scatter. Like that's kind of what dispersion is. It's looking at where you are located and relevance to like the center, the mean, okay? So the first thing we're going to talk about with measures of dispersion is the range. You guys know the range. We've been working with it for a long time. It's just the maximum value minus the minimum value. Now on Excel, there is not a range function. Like you can't type in equals range. Why? I don't know, because that's kind of shady. But we do know that it is the maximum minus the minimum. Now sometimes in our data values, it's easy to just like organize it and say this is from smallest to largest, then we can take this cell minus this cell. But sometimes we need our data values to stay in the order that they were given to us in. And if that's the case, you can just say equals maximum value of the cell range, close the parentheses, minus minimum value of the cell range, and that'll give you the range. So even though there's not like an actual function, we know enough about range to figure it out on our own. So I'm okay with that. Now the variance is the next new thing that we're going to talk about. The variance measures how the data varies around the mean. So I am a visual person, and this is how I visualize variance. So if this was the mean, and then all of my data points were varying around it, it would be like data points are varying around the mean, how close or far away they are to the mean. Or if we were talking about items and maybe not numbers, it wouldn't have to be so linear. It could be here's my mean, and here's how my data varies around it. Is it close or is it far away? Does that make sense? Okay. Now, the first thing we're going to talk about is population variance. Now just a reminder, population and sample, you're going to have different formulas. So the population variance, you're going to have all of these symbols. Do you guys remember what this symbol stands for? The sum. It's we call it sigma, but it means the sum. So this right here, this is a little symbol, and it's squared. It's actually a sigma. This is a lowercase sigma. This is an uppercase sigma. So this is a sigma squared, sigma squared. And when you see that symbol, sigma squared, you know that it's going to be the population, okay? So that stands for population variance. The population sigma squared is the population variance. And to find that, you're going to take the sum of, and then we have this little guy right here. Now, x sub I want you guys to understand that whenever you see an x sub I, you're just talking about a given data point. So the I represents whichever data point you're looking at, the first data point, the second data point, the third data point. So you're looking at the sum of a given data point minus mu. Do you guys remember what mu stands for? Mu, population mean. Mu stands for population mean. So we're taking the sum of the difference between a given data point and the population mean, and then they're squaring it, okay? Then we're going to divide it by capital N. Do you guys remember what capital N stood for? Population size, okay? Now just a reminder, on our last assignment we had that little box, and that's where we could had all those symbols, and that's when we first learned them. You really need to know what those stand for the test. You really need to know what they stand for. Now the sample variance is very similar to the population variance. It's the same concept, but instead of population sigma squared, we're going to have sample S squared. So if you see a lowercase sigma squared, that means you're looking at population variance. If you see a lowercase s squared, that means you're dealing with the sample variance, okay? Now, everything else is almost the same. We still have the data point minus, now x bar was the sample mean, and then the big difference here is instead of dividing by the size, like population variance, we divided it by the population size. N stands for the sample size, but what are they doing to it? They're subtracting 1. So you're dividing the sample size minus 1. So here's what we're going to do. We're just going to give an example and work through this so you guys know how it works, what it means. Here's an example. Given the following times in minutes of 6 people running a 1,000-meter course, compute the sample variance. So they're telling us right off the bat that it's sample variance, so we're going to use this guy right here. All right, we're going to use that formula right there. Now, they said the times are 5, 10, 9, 11, 9, and 7. That right there, those are our data values. So they need to go in the data column. So it would be 5, 10, 9, 11, 9, 7. Now, they didn't tell us that it had to be in numerical order. If it bothers you, go ahead and put it in numerical order. That's no big deal. But they didn't say it had to be. On Excel, you would just copy that data over, and then if you want to put it in numerical order, no big deal. Super easy. Now, to find the sample variance, we need to start by finding the deviation. You guys remember that? That's what we did last class, where we took each individual data value and found out how far away it was from the mean. Well, before I do that, what do I actually have to find? You actually have to find the mean. Now, in Excel, we would type equals average and then the cell data. But how do I do it without Excel? Add them all together and divide by how many are there? Can you guys do that for me quick? What'd you get? 8.5. Very good. So we know that the sample mean right here is 8.5. So now we're going to find the deviation, which is each individual data point minus the mean. We want to find out how far away it is from the mean. So I'm going to start with this, my first data point, x sub 1. Technically, this would be x sub 1. And I'm going to find out how far away is 5 from 8.5. So what is 5 minus 8.5? Negative 3.5, because it's 3.5 lower than the mean. Then we do my second data point. This is technically x sub 2. So 10 minus 8.5, what's that going to give me? 1.5. Then my third data value is 9. What's that going to give me as a deviation? 0.5. Go ahead and take a second and finish filling out the rest of the table. Now, just to get a little practice understanding deviation, which of these numbers is the furthest away from my mean? Which one? 5. 5 is negative 3.5 below it. Which of these numbers is the highest of my data values? That's the highest deviation. What's the highest data value? 11. Okay, cool. Now the next thing we're going to do is we are going to square that deviation. And the reason that we're going to do it has everything to do with the actual formula. So you guys have the formula up at the top of your paper. I'm going to rewrite it here since I don't have it here. So it's s squared equals the sum of each data value minus the mean squared all over n minus 1. Now we just found this guy right here, each data value minus the mean. That's literally just the deviation. That's all we did. We just found the deviation. Now what we want to do is we want to square it because we want the sum of all of those squared deviations. So the next thing we're going to do is we're going to take this guy and square it, this guy and square it, this guy and square it. Can you remind me, all of these numbers in this column are going to be what kind of numbers? Positive. So I'm going to take negative 3.5 squared, and I'm going to get a positive number, and what am I going to get? 12.25. Very good. Then I'm going to take 1.5 and square it. What am I going to get? 2.25. 0.5 and square it. What am I going to get? 0.25. Very good. 2.5 and square it. 6.25. Very good. 0.5 squared. 0.25, negative 1.5 squared, 2.25. And then what I need to do is I need to find the sum of all of these. I need to add all of these together. So again, you can see over here that I have that over here. You can see the total, which is really just the sum of the deviations squared. Can you tell me what are all of these added together? 23.5. 23.5. Now, to find the sample variance, again, I have to understand how to read and act upon this formula. So I want the sum of my deviations squared, which I just found to be what? 23.5. So that's going to equal 23.5 is going to go in my numerator, but in my denominator, I want n minus 1, which was my sample size minus 1. What is my sample size here? 6, and if I take away 1, how many am I going to divide by? 5. So tell me, what is 23.5 divided by 5? 4.7. So here's what that means. My sample variance is 4.7 squared minutes, okay? Now, if I wanted to find that on Excel, because guys, that was a lot of work. We had to put the data in, we had to find the deviation of each, then we had to square it, then we had to find the sum at the bottom, and then we had to divide that by the number in my sample minus 1. That's a lot. Instead, when you're on Excel, there is a nice little formula that you can just type in, and I have it over there on the right in the box. All you have to do is you have to type in equals, and then VAR for variance. That's how we're going to start off. And then you're going to notice that there's going to be two options, point P and point S. What do you think that those stand for? Population and sample. You have to understand, you have to be able to look at the data they give you and know, is this a population or is this a sample? And you know, based off the formulas that I gave you at the top of your page, those values are going to be different, because one of them you're going to divide by however many you have, one of them you're going to divide by one less than that. So they are going to be different. So this one we would have put var.s and then just highlighted the cell range, and you would have gotten 4.7. Now, the standard deviation is something similar, and we're going to talk about that in just a minute. So down here, it says, so the average squared deviation of the data is 4.7 squared minutes. That's what we just found. And that might seem a little weird because you're like, no, we found the variance. But I want to remind you, what is the variable representing the variance? S squared, okay? Now the reason for that is because we took the sum of the deviation and we squared it before we divided by the number minus 1. We took the sum of the deviation and squared it before we divided, which means that that number 4.7, that variance, is really a squared deviation. But that doesn't make much sense at all. The average squared deviation is 4.7 squared minutes. Do we measure things in squared minutes? No, that's a very weird measurement. That's a very strange measurement. That doesn't make any sense. That's where standard deviation comes into play. It takes that variance, that squared deviation, and it converts that measure into the original unit, so it makes more sense, okay? So the standard deviation is a measurement of the average deviation from the mean to the relation, or in relation to the data values. That's a really important definition. I want you guys to either highlight that, circle that, make note of that. The standard deviation is a measurement of the average deviation from the mean in relation to the data variables. It is found by taking the square root of the variance. So this is really important. If you've already found the variance, to get your standard deviation, you don't have to go through any more work of like finding the deviation and squaring it and dividing it. No, all you have to do is take the square root of that variance. That's why the variance is s squared, because the standard deviation is just the square root of that, which is s. Now, some information that we need to know about the standard deviation. First of all, it's either got to be 0 or positive. And the reason for that is obviously because we're taking the square root of something to get it. You cannot have the square root of something and get back a negative number, so it's either going to be 0 or positive. The standard deviation can be impacted greatly if outliers are in the data. So if we have outliers, remember last class we talked about that example with the test grades, if we have outliers, it's going to impact the standard deviation, so that means this is not a resistant measure. It is not a resistant measure. And then finally, standard deviation is expressed in the same units as the original data values. That's the whole point of it. We want to get from those minutes squared back down to the regular original measurement. Now, on Excel, there is formulas for it, and it's the same thing with the variance. If you start typing in equals STDEV, you just have to choose if it's population or sample, and then highlight your cell range, and it'll give it right to you. Cool? All right, go to the back page. Now, the next thing we're going to talk about is the empirical rule. You guys have seen this before. If the distribution of the data is bell-shaped, okay? So if you make a bar chart, a table, a histogram, whatever, of your data, and it comes back looking bell-shaped. Now, you guys know that sometimes it's not perfect, but it's pretty close to being a bell-shaped, which means it's higher in the middle, and then it gets smaller off to the sides. That means it's going to follow the empirical rule. And the empirical rule is also known as the 68, 95, 99, 7 rule. So 68% of the data should lie within one standard deviation of the mean. 95% of the data should lie within 2 standard deviations of the mean. And 99.7% of the data would lie within 3 standard deviations of the mean. Now, another thing that they call this is the 1, 2, and 3 sigma rule, because standard deviation is just sigma. But here's what it means. In your bell-shaped curve, okay, your mean lies where? Directly in the middle. Okay, that's your mean. What we're going to do is we're going to call that 0. 0 is going to represent our mean, okay? Now, 68% of the data would lie within 1 standard deviation of the mean. So here is 1 standard deviation, and here is 1 standard deviation. So if I am 1 standard deviation higher than the mean, or 1 standard deviation lower than the mean, 68% of my data, 68% of my data lies in that section right there. Are we okay with that? 95% of the data is going to lie within 2 standard deviations of the mean. So if I go 1 standard deviation this way, and then I go another standard deviation this way, that would mean I'm 2 standard deviations away. And the same thing this direction, I would be negative 2 standard deviations this way. That means 95% of my data is going to be in that section right there. And then if I go 1 more and get 3 and 3, I'm going to have 99.7% of my data within 3 standard deviations from the mean. Okay? Now, we are going to use this a lot this semester. This is a really, really helpful visual. So to do that, I'm going to put as much information as I can into this picture. So I have a question. If this is my mean right here, if this is my mean, and I know that 68% of the data lies within 1 standard deviation from my mean, what percentage of the data would lie between my mean and 1 standard deviation above it? 34%, right? Wouldn't you just split it in half? So what would this section right here be? This would also be 34%. So 34% of my data is in this section, 34% of my data is in this section. Okay, now 95% of my data lies within 2 standard deviations of the mean, so we're going to have to think a little more or a little harder on this one. We know that from 0 to 2 would be what percentage of my data? From 0 to 2 would be what percentage of my data? 40, 47.5? Okay. So then what percentage is just in between 1 standard deviation and 2 standard deviations? How do I get that? Ooh, 13.5. How'd you get that? Very good. So over here, this would also be 13.5. This would also be 13.5. See if you can figure out between 2 and 3 on your own. So what percentage of my data lies between 2 and 3? 2.35 and 2.35 over here. Just a reminder, how you get that is you take the 99.7 minus 95 and divide it in 2. And then what about these tails? If I have 99.7% of my data in from -3 to 3 standard deviations, what percentage is left to split between those two? 0.3. So if I split it between those two, what's going to be over here? 0.15? Yes, sorry. I don't know why I have a 0 in there. 0.15 and 0.15. And remember, that's percent. 0.15% would be more than 3 standard deviations from your mean. Now, there's one more thing I want us to do to this table to help us understand what the heck is going on, and that's to just put a little bit more information so you know what these 0, 1, 2, and 3 mean. 0 doesn't mean you have the number 0. 0 is representative of your mean. This is your mean, whatever it is. Okay, that's your mean. 1 means I'm going to have your mean plus 1 standard deviation. Okay? 2 means I'm going to have my mean plus 2 standard deviations. 3 means my mean plus 3 standard deviations. Same thing with -1. That would be my mean minus a standard deviation. -2 means my mean minus 2 standard deviations, and mean minus 3 standard deviations. That's what 0, 1, 2, 3, -1, -2, -3 mean. It's not a number, it's representation of how many standard deviations I am from the mean. Okay? Now, let's talk about problems where that's going to help me. How does this apply to statistics and how I'm going to use it? So, my first example down here, it says, suppose a group of high technology stocks has an average earnings share of $6.26 with a standard deviation of $1.37. If the data possesses a bell-shaped distribution, find the interval that contains 68% of the earnings. So you're going to have a lot of problems like this today. Here's the best way to solve them. They're telling you that it's going to be a bell-shaped distribution. The first thing you should do is just come over here and do your best to sketch a bell-shaped distribution. It doesn't have to be perfect. I mean, it is what it is. And then you know that the mean goes in the middle, and you're going to go ahead and put 1, 2, 3 lines up, and 1, 2, 3 lines down. Now, we know that this would be 0, 1, 2, 3, -1, -2, -3, but what that 0 represents is my mean. Did they tell me what the average or the mean was in this problem? $6.26. So that's actually going to go in the middle. That is my average for this problem. Now, it says we have a standard deviation of $1.37. So if I wanted to figure out what 1 is, I would take this 626 and I would add $1.37. And what would I get? 763. And then if I wanted to figure out what 2 was, I would add another $1.37. So what is 763 plus $1.37? $9. And then my 3 over here would be plus another 137, which would be 1037. Right? Now to get these over here, we're going to do the same thing, but we're just going to go the opposite direction. So 626 minus 137 would be what? 489. Then we're going to subtract 137 again, and what do I get? 353? No, 352. And then we're going to subtract it one more time, and what do we get? 215. So that's what an empirical rule would look like for this problem. The mean is in the middle, and then the standard deviation. So I want you to think about what that means in relation to this problem. Suppose a group of high technology stocks has an average earning per share of $6.26. So per share, on average, you're going to earn $6.26. But they do have a standard deviation of $1.37. So you can earn more and you can earn less per the share, but those are standard deviations. So if you earn $10.37 per share of the stock, is that going to seem very likely? Like, do you think that's really going to happen? No, the chances of that happening is not very high. So it says, if the data possesses a bell-shaped distribution, we just drew that, find the interval that contains 68% of the earnings. Now, if we go back and look at our little guy up here, 68% was within one standard deviation. That's the first sigma rule, the 1 sigma rule. So within one standard deviation is this guy right here. What is the interval that contains 68% of the earnings? Good, 489 to 763. That means 68% of the earnings from the share are within $4.89 to $7.63. Let's go to the next one. Suppose the shoe sizes of American women have a bell-shaped distribution with a mean of 8.06 and a standard deviation of 1.52. Using the empirical rule, what percentage of American women have shoe sizes that are less than 11.1? So, again, they say using the empirical rule, they tell you it's a bell-shaped distribution. Let's sketch that out. And we're going to put in the measurements here. We know that I'm going to have 1 in the middle, 3 more, and 3 less. And what measurement goes with the middle? 8.06. And it has a standard deviation of 1.52. So you know you're going to have to add, and add, subtract, subtract, and subtract. However, let's think about it in terms of this problem. Maybe I don't need to find all of those measurements. Maybe that's not necessary. It says, using the empirical rule, what percentage of American women have shoe sizes that are less than 11.1? So I really need to focus on this 11.1. So do I need to worry about the standard deviations that are below 8.06? No, just the ones that are above it. So what's one standard deviation higher than 8.06? 9.58? And then, is that 11.1 yet? No, so I'm going to go one more. What is 9.58 plus 1.52? That's 11.1. So that's where I'm looking at. That's what I can stop at. But it says, what percentage of American women have shoe sizes that are less than 11.1? So I want to know what percentage is less than 11.1. I want to know what is all of this over here. So you have a couple of different options here. You could sit here and say, what is this plus this plus this plus this plus this plus this? That would work. You could also say, all right, I know that this 8.06 has to be what? What percentage? It's the average, it's the mean. It's in the middle. 50. So up to 8.06 is 50%, then you could add this and this. That would work. Or you could just take 100%, because you know that it has to be 100%, and take away this one and this one. So you have a couple of different options there. Now to figure out what this guy and this guy equals, you can either look back up at the top, where we kind of put those measurements in each one, or you can do the figuring. It literally is whatever is most comfortable with you. Now, we're going to prepare for a test where I'm not giving this to you. You just have to understand how it means. So let's do it without the little guy up top. I'm going to try and figure out what these two guys stand for, or what they represent. So I know that this is 68%, and this is 95%, and this is 99.7%, right? So to figure out what this guy is, I want the 99.7 minus 95, which is going to give me 4.7, then divide it by 2, and what did that give me? 2.35. Then this guy right here, since this was 99.7, we wanted to take the 100% minus 99.7, which got me, do you guys remember? 0.3, divide that by 2, and that gave me 0.15. So to figure out what this highlighted area was, we could take 100 minus 2.35 minus 0.15, and what do we get? 97.5%, which means 95.7%, or 97.5, goodness, 97.5% of American women have shoe sizes that are less than 11.1. Knowing, especially you females, knowing what you know about shoe sizes, does that seem normal? Does that seem accurate? Absolutely. If you're a woman with a size 11 shoe, you have a pretty big foot. Not very many women do. So, about 97.5% of women have something smaller than that. Now, the last thing we're going to talk about is the coefficient of variation. And here's where that comes in handy. It says, what if we have 2 or more data sets that we want to compare their variations? This is where the coefficient of variation comes into play. It is a unit free. There is no unit. It doesn't matter if you're comparing centimeters and miles. It is unit free. And it enables the comparison of variation from different sets. So I have 2 different things down here, but I want you to look at them, population and sample, the coefficient of variation. What does this little sigma represent? That's standard deviation divided by mean times 100%, right? Well, over here for the sample, it's the same thing. Standard deviation divided by mean times 100%. Okay? So here's how this is helpful. A bolt manufacturer wants to compare the variability of 2 bolt manufacturing processes. One process creates bolts with a mean length of 2.5 centimeters and a standard deviation of 0.2 centimeters. The other creates bolts with a mean length of 1 inch and a standard deviation of 0.052 inches. So we want to compare these 2 bolts, but they're in completely different measurements. That's where the coefficient of variation comes in play. So I'm going to highlight information that goes together. You guys can underline or whatever. The first bolt has a mean length of 2.5 centimeters and a standard deviation of 0.2 centimeters. And the other bolt has a mean length of 1 inch and a standard deviation of 0.052 inches. I really want to know, how do they compare to one another? All right? So I'm going to call the red guy group A, and I'm going to call the blue guy group B. Okay? So the red guy is group A, and the blue guy is group B. And what I'm going to do is I'm just going to find the coefficient of variation for each of them. So to find the coefficient of variation, first and foremost, are these samples or populations? I would say they're samples. So we're going to take the standard deviation and divide it by the mean. So what's the standard deviation here for group A? 0.2, and we're going to divide it by the mean, which is 2.5, and we're going to multiply that by 100. That's all we're going to do. Okay, we're going to multiply that by 100. So in our calculators, 0.2 divided by 2.5 times 100, 8. And remember, that turned it into a percent, so that's 8%. Okay, that's 8%. And we're going to interpret that in just a minute. Let's do the same thing for group B. I'm going to do the same thing, coefficient of variation. We're going to take the standard deviation, 0.052, and divide it by the mean, which is 1, multiply it by 100, and you don't even need a calculator for that. What's that going to be? 5.2%. Now, the bigger the percentage, I want you to think about this. We're talking about a coefficient of variation. The bigger the percentage means that there is going to be a larger spread. Bigger percentage means there is a larger spread. smaller percentage means that there is a smaller spread. So when they say a bolt manufacturer wants to compare the variability of two bolt manufacturing processes, which one looks more accurate, A or B? B, it has the smaller spread. Their measurements are closer together than A, which has a larger spread. Their measurements are further apart. Do we understand? All right, homework's on Hawks.